For the demonstration, we selected a plug-in electric vehicle, a Hyundai Kona EV from the Birmingham Centre for Energy Storage at the University of Birmingham. Its rear suspension dimensions are comparable with the Electro-Intrusion shock absorber prototype, making it an ideal test platform. To minimize the influence of the original commercial dampers on the prototype's performance, both rear shock absorbers were replaced with our Electro-Intrusion prototypes. In the Kona's rear suspension, the coil spring and damper are separated. This makes installation simple. By removing just 2 bolts from the top mount and 1 from the control arm, the commercial unit can be swapped for our prototype without touching other components. All cables, including those from the pressure and displacement sensors inside the prototype and the force transducer at the top mount, are combined into a single CAN bus wire, leading to a Picolog data taker in the boot. To maximize the harvesting of the fluctuating electrical output from the prototype, we developed a dedicated energy harvesting circuit designed for heterogeneous power scenarios. Its core is an adaptive maximum power point tracking algorithm that converts irregular voltages into a stable 1.8 volt DC output with a theoretical transfer efficiency of 99.8%. This technology has been under development since 2022. After 4 generations of hardware testing, circuit design, and algorithm optimization, it has evolved into an integrated compact PCB with a self-developed algorithm capable of millisecond-level response and more than 99% conversion efficiency. Multiple sensors were installed on both the demo car and the prototype: a voltage and current recorder to monitor electrical output, a force transducer connected to the top mount, a laser distance sensor for stroke measurement, 2 fluid pressure sensors inside the cylinders, and 2 cameras, 1 for the road surface and 1 for the prototype's real-time operation. This section shows the functional check of the sensors and the clearance verification of the installed shock absorber prototype. We first carried out a slow drop-off test from a 150mm step. The rear wheel descended at a controlled, almost quasi-static speed. As it stepped down, the shock absorber extended sharply, producing a rebound pressure spike, followed by bouncing and then compression. That's why we see the rebound voltage rise first, followed by the compression voltage increase. This signal confirms good performance under large suspension travel. The road test was conducted on a closed test track with a 70mm high-speed bump. The vehicle speed was 10 miles per hour. Real-time data are displayed in the upper left corner. Let's replay the same test for clearer observation. As the vehicle passes over the speed bump, the sensors record a distinct waveform peak. We will now analyze it in slow motion. This slow motion replay was captured by a high-speed camera at 1/20 of real-time speed under the same test conditions. When the wheel first contacts the speed bump corresponding to this point, the prototype shock absorber is compressed. The displacement curve rises, and the fluid pressure inside the compression cylinder increases, generating the electro-intrusion effect and producing a voltage signal at the output. When the damper reaches maximum compression, the peak of the displacement curve, its motion reverses from compression to extension. The pressure in the compression cylinder decreases, while the opposite cylinder's pressure rises. During this pressure release, the voltage signal disappears, corresponding to the extrusion behavior. At the negative peak of the displacement curve, the motion reverses again from extension back to compression, and the fluid pressure in the cylinder starts to decrease accordingly. We performed road tests under controlled conditions, varying speed bump shape, height, crossing speed, and payload. As shown in this 3D chart, higher speeds and taller bumps produce stronger electro-intrusion responses, with peak outputs around 20 to 23 millivolts. with a 100 kg payload, the overall trend stays the same. The additional weight noticeably enhances the output for small bumps, because the suspension settles lower and engages more of its available travel, even under mild excitation. For larger speed bumps, the effect becomes much smaller, as the speed bump already drives the suspension through most of its natural motion range, leaving little room for the payload to introduce further change.